Nicolas Andrushkiewicz from University of Cordoba, and he will speak about on the double of the Jordan plane. Please.
Thank you. Thank you, Slava, for the invitation. It is really good to be here and meet some people after 2-3 years that I have not seen. Even people from Cordoba that I have not seen in 3 years. Okay, so I would like to report on some joint work with François Dumas from Clermont-Ferrand, Héctor Martín Peña Polastri, former PhD student of mine, and 3 colleagues from the Universidad de Santa María, Dirceu Bajo, Saradia de la Flora, and Diana Flores. What we are trying to do is to understand a new Hopf algebra, which is not so big, but I will explain why we are interested in this precise example of Hopf algebra a bit later. And the basic input for the construction of this Hopf algebra is the so-called Jordan plane. So to start with, let me say that K will be an algebraically closed field, and except for the last section, the characteristic of K will be either odd or 0. Now the Jordan plane, I don't know who introduced this algebra. It's an algebra known for a lot of years. It's a quadratic algebra, meaning that is presented by generators and relations, and there is only one relation which has degree 2. So formally is the algebra generated by x and y with relation yx minus xi plus 1/2 x squared. Then the 1/2 is, of course, could be absorbed, but it's better to keep it for aesthetical reasons. And one instance where this algebra appeared, it was in the work of Artin and Schelter in the 80s. They were looking to a kind of analog of polynomial rings in the world of non-commutative associative algebras, and they wanted to have something that will play the role of the projective space, a quantum projective space or non-commutative projective space. And they came with the definition of ace-regular algebras. So they are domains with finite Gelfand-Killian dimension and a lot of homological properties that I will not recall here. And they classified those with Gelfand-Killian dimension 2, and they showed that they are there is a family of quantum planes and the Jordan plane. So this is one instance where the Jordan plane appeared. By the way, the Gelfand-Killian dimension of an associative algebra is I don't have time to explain this technically, but it's a dimension that is the natural extension of a Krull dimension of an algebra. So if you want to do some non-commutative geometry, you need some dimension as a first input, and the input is this, the Gelfand-Killian dimension. Now, for us, what is important is that the Jordan plane has another structure, which is so-called braided Hopf algebra. So what is a braided Hopf algebra? A braided Hopf algebra is an algebra with the multiplication and the co-multiplication, but the usual compatibility of the multiplication with the co-multiplication is twisted by something called the braiding in some way. I don't want to go into details because it's not important for what I will do, but I simply will remind that a braid equation is this, is given an invertible linear map from V tensor V to itself. We say that C is a braiding, or that it satisfies the braid equation if it satisfies this. So this is equivalent to the quantum Yang-Baxter equation, and this is the reason why quantum groups entered into the picture. And Gurevich observed in the 80s also that if you take a vector space V with the basis xy, and you define a braiding in the basis by these rules, then this is a solution of the braid equation. And from there, he proved that the quantum plane is a braided Hopf algebra in the imprecise meaning that I gave before. Actually, also some technicality that is not completely needed. V is more than a braided vector space. It's a Jeter-Drinfeld module. It means that it's a gamma over the abelian group isomorphic to zeta. And this means that this is a gamma-graded gamma module. The grading of V is just the generator G. And the action is given by G acting on X and equal to X, and G acting on Y is equal to Y plus X. In other words, this is action by a Jordan block with ones in the diagonal. And then the fact that V is a Jeter-Drinfeld module implies that G is a Jeter-Drinfeld module, and then we can form the bosonization, and we can forget about everything what I said. You just need to consider that we are looking at this algebra, the algebra H tilde, which is generated by 4 elements, x, y, g, g minus 1, with these relations. So these relations reflect the action of G. This relation on X, this is the action of G on Y, and this is the relation coming from the Jordan plane. And the commultiplication of this Hopf algebra is given by this formula. So G is a group-like, and X and Y are G1 primitives. So we call this the bosonization of the Jordan plane. Okay. Now Nichols' algebras enter into the picture. Essentially, this says that Nichols' algebra is a quadratic algebra like J, and the difference, the new axiom is that all primitive elements are in degree 1, so are in V. And this happens when the characteristic of K is 0. And this was observed, to my knowledge, first in a paper by Sibils, Lowe, and Witherspoon. And when we started to look at the problem of classifying Nichols' algebras with finite Gelfand-Kirchhoff dimensions some 10 years ago, we started with the blocks. So what is a block? A block is a vector space of dimension L with the basis x1, xl, such that C of xi tensor xj, if j is 1, is epsilon x1 tensor xi, and if j is bigger than 1, is given by this formula, epsilon xj plus xj minus 1 tensor xi. In other words, this is a Jeter-Drinfeld module where over the group gamma isomorphic to zeta, where the generator G acts by a block. And we were able to prove that the Gelfand-Kirchhoff dimension of the Nichols algebra of such a block is finite if and only if L is equal to 2 and epsilon is plus or minus 1. And so there are two important blocks for us, those that have finite Gelfand-Kirchhoff dimension. One is the Jordan plane, corresponds to epsilon equal to 1, and the other corresponds to epsilon equal to minus 1, and is called the super Jordan plane. The super Jordan plane, we found, had this presentation. It has an element which is nilpotent of degree of nilpotency 2, and a cubic relation, because x21 is this anti-bracket, x2, x1 plus x1, x2. So this has degree 3. In particular, observe that the Jordan plane is not a domain, so it's not AS regular, and it has Gelfand-Kirchhoff dimension 2, because it has a PBW basis also. Okay. So I would like to focus on the Jordan plane in the main part of the talk. The result of this classification of blocks with finite Gelfand-Kirchhoff dimension was important for us, for we were trying to classify Hopf algebras with finite Gelfand-Kirchhoff dimension, and for that we started looking at the class of radial vector spaces which are direct sums of blocks and points. And the only blocks we have to consider are those in the previous slide. And we obtained the partial classification, so very complete for one class, and for all abelian groups it's not yet finished. And we want to understand the Nichols algebras and associated Hopf algebras associated to this construction, to this classification. And we started by the Jordan plane because it's the easiest example, and this is we need to understand the representation theory of the Jordan plane before going on to the more general cases. Another observation is that in many papers, in a couple of papers, we observed that these braided vector spaces, which I am not describing, but that they appear in the classification, also give rise to finite dimensional Nichols algebras in positive characteristic. So I forgot the phrase positive characteristic. So let us start with the Jordan plane in odd characteristic. So what I want to do is to define the Drinfeld double of the Jordan plane. So I start with the Drinfeld double of the restricted Jordan plane. What is the restricted Jordan plane? Assume that the P, the characteristic of K is odd. Recall that our V has a basis X and Y with the braiding given by these formulas. Then Sibyl, Slove, and Witherspoon observed that the Nichols algebra B of V is the quotient of T of V by the ideal generated by three relations, X to the P, Y to the P, and this which is the relation of the Jordan plane. In other words, the Nichols algebra of V in characteristic P is the quotient of the Jordan plane by these two relations, these two extra relations. So by analogy with the theory of restricted Lie algebras, we call this the restricted Jordan plane in characteristic P. Okay. As before, we can realize V as a yet a Drinfeld module over the cyclic group Cp of order P. And as before, we can form the bosonization of H of B of V with the restricted Jordan plane with the cyclic group. And then we observe that this is easy to see. How to construct it is easy to see from the relation, and how is the comultiplication is also easy. And we have a surjective map of Hopf algebras from H tilde to H. Okay, this is not the algebra we're interested in. We're interested in the Drinfeld double. So what is the Drinfeld double? Suppose that L is a finite dimensional Hopf algebra. Then Vladimir Drinfeld introduced the double of L. This is a new finite dimensional Hopf algebra, which is as vector space or as a coalgebra is double L, so it's L tensor L dual op. This is and the algebra structure is a kind of semi-direct product in both ways. And it is quasi-triangular, meaning that any module, here it's a mistake, any module over the double of L comes with the solution of the braid equation. So this, in other words, given any Hopf algebra L, the double of L is a machine to construct solutions of the braid equation or of the quantum Yang-Baxter equation. Actually, the category I did not want to define precisely, the category of Vieta Drinfeld modules over L, is equivalent to the category of left modules over the Drinfeld double. And the construction of the Drinfeld double of L is very specific, so we performed it for our H, and we obtained this. We obtained that the Drinfeld double D of H is generated by three elements, G, X, and Y, which are generators coming from H, U, V, and zeta, which come from H dual, and they satisfy these relations. Okay, these relations which are in red are those that ensure that we have finite dimension. Zeta here is not a group character anymore. It's not a group-like anymore, but it's primitive. This is the difference with the usual constructions. So we have zeta commutes with G, and we can group G and zeta and have a triangular decomposition of this algebra D of H. And then we have the relations. These are relations coming from H. And then this is coming from H. This is coming from H dual, so we had to compute H dual to begin with, and so on. So, okay, so this is a mass of relations, and any hope to work with this and obtain anything meaningful, it's very slim. So we try to understand this in another way. And, well, here is the co-multiplication. As I said, zeta is primitive, and V is not skew primitive. It's in this next step of the co-radical filtration. And to understand better D of H, let me recall what is a short exact sequence of Hopf algebra. This is a collection of 3 Hopf algebras and 2 maps of Hopf algebras, iota and pi, where iota is injective, pi is surjective. The kernel of pi is the left C ideal generated by the augmentation ideal of A inside here. And this means that A is normal in C, and then there is this condition that A coincides with the co-invariance of pi. This says that B is co-normal quotient of C. So we need, these two relations are dual to each other as one needs in the theory of Hopf algebras. When A is commutative and B is co-commutative, we say that the extension is abelian, because in this case we have a kind of classification of the extensions in cohomological terms. Now, let me recall or convene that H, A, and F are the Cartan generators of SL2K. SL2K, wherein characteristic P has an enveloping algebra, but also has a restricted enveloping algebra denoted small u SL2K. This small u means restricted, and this is the usual universal enveloping algebra divided by the p powers of H, A, and F. Well, more HP minus H, A to the P, F to the P. And we have proved the following. Suppose that you take the subalgebra R of D of H. So remember, D of H had generators G, X, Y, U, V, zeta. Then take R, the subalgebra generated by G, X, and Y. This is a normal Hopf subalgebra. It is commutative and has dimension P cubed, and has these defining relations. And if you take the quotient of R by D of H, in the sense of Hopf algebras, what you get is a small restricted algebra of SL2K, where concretely pi sends zeta to H, Y to 1/2 of A, and V to F. So, and somehow surprisingly, in the middle of this bunch of equations, we could describe D of H in this better way. Now, as I said, R is normal and local. Therefore, we can obtain the following result, essentially coming from the Jacobson theorem, that the irreducible representations of D of H are the same via pi, are isomorphic to the irreducible representations of the restricted enveloping algebra. Hence, there are exactly p isomorphism classes of simple DH mod, but this are well known. They are p-isomorph classes of simple DHF modules because they are p-isoclasses of E-reps of U of SL2K, and they have dimensions 1, 2, 2p. And I said before that D of H has a quasi-triangular structure, meaning that you can split it in 3 parts, like positive nilpotent, 0, and negative nilpotent. And there is a theory of Verma modules. And using this theory of Verma modules, we can also construct explicitly these representations of D of H. Okay. Then we said, okay, now we understood what is the Drinfeld double in characteristic P. Let's go back to the Jordan plane. So the input for the previous construction is the restricted Jordan plane. Let's go to the Jordan plane. And in the case of the Jordan plane, we make the following definition. The double of the Jordan plane is the algebra D, which is the main object of this talk. This algebra G is generated by similar elements as before, G plus or minus 1, X, Y, U, V, and zeta. But if, let me remind you, we had this lot of equations which I numbered 1, 2, 3, 4. One are the red ones that they ensure finite dimensionality. And we, for the definition of the Hopf algebra D, we keep 2, 3, 4 and replace 1 simply by asking G to be invertible. And the same formula for the commultiplication is valid here, meaning G is a group like, U and zeta and primitives, X and Y, G1 is Q primitive, and V has this formula. Delta of V has this formula. So this is the double of the Jordan plane, and I will describe the relation with the previous slide in a moment. For that, we need to introduce some notation for algebraic groups. So GA is the additive group. This is the additive group K plus. GM is the multiplicative group, K minus 0 with the multiplication. H3 is the Heisenberg group of dimension 3. G is, I let add GM on the direct product of 2 copies of GA by some action which I don't want to tell you. And B is G times H3. Another notation I will use is O of G for me is the algebra of regular functions on an algebraic group G. Okay. Then, parallel to what I said before, we can prove that, first, the subalgebra of D, which is this so-called Drinfeld double of the Jordan plane, not finite, the real Jordan plane, I take the subalgebra as before generated by X, U, and G. This is a normal Hopf subalgebra, is isomorphic to O of G. G was the group introduced in the previous slides. And this isomorphism is as Hopf algebras. On the other hand, I have a map pi from D to the real enveloping algebra U of SL2K, given as before by X going to 0, Y going to 0, G going to 1, and this is the same rule as before. And we have the following proposition. There is an exact sequence of Hopf algebra where O of G is, there is a map iota. Well, this iota comes from the isomorphism here, and this pi already described it. As you put them together, you get an exact sequence of Hopf algebras. So to understand D, this is much better than the set of relations. Furthermore, assume that, so this construction is for any characteristic different from 2. Now assume that the characteristic is odd. Then we can combine these two constructions in the following sense. This is the exact sequence for the Drinfeld double of the restricted enveloping algebra, of the restricted Jordan plane. This is the exact sequence of corresponding to D, constructed D as O of G to SL2. This is the so-called Frobenius map, so this is the kernel of the Frobenius map. This is a kind of Jordan Frobenius map, and this is the kernel in the sense of Hopf algebras, and the same is here. So there is 9-term square where all columns and all rows are exact sequences of Hopf algebras. So I don't know how we will apply this, but I was very happy to see this picture. Some properties of D, assuming that the characteristic is 0. First of all, this algebra D admits an exhaustive ascending filtration Dn, and the associated gradient algebra is a tensor product of the Laurent polynomial in one variable with a polynomial ring in 5 variables. From there, it comes at once that D is an Ethereum domain. It can also be shown, looking at the relations, that D is an OR extension, an iterated OR extension. And from there are some important properties, like D is strongly Noetherian, meaning that when you extend scalars, it remains Noetherian. A is regular and Cohen-Macaulay. So these are cohomological properties, and they come from the fact that the associated graded ring has this beautiful shape. Also, D is a PI algebra and satisfies the Gelfand-Kirillov property. The Gelfand-Kirillov property means that the skew field of fractions of D is isomorphic to a Weil skew field. This is a property that appeared in the same paper where Gelfand and Kirillov introduced their dimension. Now, here we have this diagram. In this extension, R is local. And then the irreducible representations, as I already said, of D of H are in bijective correspondence with those of U of SL2. But here, O of G is not local. So we discussed with Hector a lot about whether this map will be an irreducible bijection between the irreps of D and the irreps of U of SL2K. So a priori, there is no reason why this will happen. So no obvious reason, at least for me. But we were able to prove that the irrep of D is isomorphic to irrep of big U of SL2K. And the proof uses the following result. Suppose that you have an algebra and the family of elements satisfying that they commute with each other, and any element in this family F acts nilpotently in any A module, and also that F is normal. It means that the ideal generated, the left ideal generated by F is a two-sided ideal. Then any representation of A factors through A divided by the left ideal generated by F. So that the projection from A to A divided by AF induces a bijection between irrep of A and irrep of A divided by AF. And once, well, of course, this lemma we obtained it at the end. What we did first was to check that F has this hypothesis, and then observe that the hypotheses have to be organized in that way. Okay, another theorem we obtained about the structure of D is that we computed the center. The center of D is the commutative subalgebra generated by 3 elements zeta, omega, and theta. The elements zeta, omega, and theta are constructed using two auxiliary results, two auxiliary elements Q, Q and S, and they live in frac of D, but actually we can show that they live really in D, and they generate the center. So this theorem is proved with techniques of localization, non-commutative localization. Okay, so now I go to the last two sections of my talk are about the super Jordan plane and in its restricted version in odd characteristic, and the Jordan plane in even characteristic. For the super Jordan plane, I will again assume that the characteristic is different from 2. Again, I take a V with basis xy, and such that the braiding is given by this rule. C of x tensor x is minus x tensor x. C of y tensor x is minus y tensor I. C of x tensor y is this expression minus y plus 6. C of y tensor y is minus y plus 6 tensor y. So this is similar to the previous braided vector space that we used for the Jordan plane, but the minus sign appears here. So I explained this is the epsilon block with the epsilon is minus 1. And the super Jordan plane, let me remind you that is defined by this rule, where x1 squared is 0, and then you have this cubic relation. And I call it S of G. As I said before, we proved that when the characteristic of K is 0, the Nichols algebra B of V is isomorphic to the super Jordan plane. And if the characteristic of K is P, is odd, then the Nichols algebra B of V is the super Jordan plane divided by 2 elements. One is the power of x21 to the P, which is expectable, and by, well, a bit surprising, we understood later why x2 to the 2 times P is 0. So the powers are like this. And therefore, we have a PBW basis with x1, x2, and x21. And because of these powers and this power, the restricted super Jordan plane has 4 times P squared. So we want to play the same game as before for the super Jordan plane. And in particular, we want to understand why this is super. Again, assuming that the characteristic is odd, we realize V as a Jeter-Drinfeld module over the cyclic group of order 2p. We need 2p because here we have this. So then we have to take the cyclic group of order 2p, otherwise you cannot realize it. Then we form the bosonization, and this is the algebra with these relations. So this is the relation of the action on gamma on x, the action on gamma on y. This is C2p. These are the relations of the super Jordan plane. I think I repeated it once. This is repeated. Okay, and the dimension of this guy is this is a mistake, is 8p squared, because the preceding was 4p squared, then we have to add 2p, is 8p cubed. This 4 is not correct. The co-multiplication of this Hopf algebra says that gamma is a group-like element, and x and y are gamma 1 primitives. Okay, so this is more or less easy. And there are a couple of facts. I didn't want to give you all the details because I gave them already for H. And the first fact is that the Drinfeld double can be computed explicitly. This is not surprising. And when you compute the Drinfeld double, you have too many group likes of order 2. So the first reduction is we take D of H and observe that it has a normal Hopf subalgebra generated by a group like of order 2, and we divide, in the sense of Hopf algebras, D of H by this normal Hopf subalgebra. So we took away one group like of order 2, take away one, and we call the resulting algebra D. From this D, we observe that this D is the bosonization of a Hopf superalgebra D, calligraphic D, with C2. This is how one goes from Hopf superalgebras to Hopf algebras. Okay, so to understand D of H, we are reduced to understand this calligraphic D. So for this calligraphic D, we observe the following. Let R be the supercommutative Hopf superalgebra generated by 3 elements, x1, x2, and t, with relations x1 to the p, x2 to the p, tp minus 1. So this is commutative, this is the even part, and this is the odd part, is the exterior algebra of y1, y2. So as I said, x1, x2, and t at even, y1, y2 are odd, and the co-multiplication of this Hopf superalgebra is given by these rules. So y2 is primitive, y1 is t1 primitive, t is group-like, and these have these strange formulas. And what we can prove is the following. There exist the Hopf superalgebra maps Y and P. Y realizes this R as a Hopf superalgebra of D, so D was in the previous slide, and pi is a projection of D onto the restricted enveloping superalgebra corresponding to the restricted Lie algebra OSP12. So again, we were a bit surprised that out of nothing, it appeared this old algebra OSP12. Now, as before, R is finite dimensional, local, and normal, and then we conclude that the irreducible representations of D are in bijective correspondence with the irreducible representations of the restricted enveloping algebras of OSP12. And those were computed in the literature. I forgot the authors. And it turns out there are p-isomorphism classes of simple D modules which have dimensions 1, 2, 3, 5, so all odd numbers at up to 2p minus 1. And again, there is a 9-term diagram where all columns and rows are exact. I don't want to enter into detail on this because it's already too technical, but here on the bottom we have the exact sequence I described before. It turns out that this D comes from a map Hopf superalgebra D tilde. In the same way you, as before, you just take out the powers. This the tilde comes also equipped with an exact sequence where this is an algebra of functions on an algebraic supergroup, and this is U of SP, and this is the Frobenius map. This is the kernel of the Frobenius map, and here we have also kind of Jordan Frobenius map, and here also. Okay, we did not study yet the algebra D tilde in the same way as the algebra D for the Jordan plane. Now, we can also say something about the restricted Jordan plane in even characteristic, in characteristic 2. And this is joint work with Dirceu, Saradia, and Diana. In this case, let me recall that again, our starting point, our input, is the vector space V with braiding given by this formula. So this is like at the very beginning. C of x tensor y is y tensor y plus x. Y tensor y is y plus x. So here, 1 and minus 1 are the same. And one would expect that this will behave like the Jordan plane. But the super Jordan plane is closer to the Jordan plane characteristic 2 than the before. Actually, this starts with a theorem by in the same paper, Sibyl, Slove, and Witherspoon observed that the Nichols algebra, B of V in characteristic 2, is the quotient of T of V by the ideal generated by the following relations. x1 squared is 0, x2 squared is 0, so this is similar to what we had before in the super case. In super case, we had x2 to the 2p is 0, so it's the same. Then we have this relation. This is a cubic relation, which is the analog of the cubic relation for the super Jordan plane. And then we have this relation, which is the analog of the relation x to 1 to the square equal to 0. This has dimension 16. As I said, it's closer to, I forgot here to insert the word super. So it's closer to the restricted super Jordan plane in odd characteristic. So characteristic 2 is very different from any other characteristic, and in particular the restricted Lie algebras in characteristic 2 are very different from characteristic 0. So first, as before, I can construct a Hopf algebra H, which is obtained by bosonization of B of V with the group algebra of C2. And I realize V over C2 exactly as before, so I don't enter into details. And the Hopf algebra A is explicitly defined by these relations. So G squared equal to 1 is the relation coming from C2. This is the action of G on X and G on Y, given by these two relations. And these are the relations of B of V, as computed by Sibyl, Slove, and Witherspoon. It turns out that this is a Hopf algebra. Now the dimension is 32, and G is a group like, and X and Y are G1 primitive. So I want to describe an exact sequence as before. For that, I start with an algebra S, which is, in the literature, is known as the derived Lie algebra or the four-dimensional Witt Lie algebra. To be concrete, S has a basis ABC and bracket AB equal to C, AC equal to A, and BC equal to B. So C is a kind of Cartan element, and A and B are nilpotent positive and nilpotent negative. It turns out that this is a unique, up to isomorphism, simple Lie algebra in characteristic 2 of dimension 3. Now, this Lie algebra is not restricted, so there is no map from S, kind of power map. But when you have a Lie algebra which is not restricted, you made it restricted by brute force, and this is called the minimal 2 envelope. So the minimal 2 envelope of S is the Lie algebra M, which has a basis ABC as before, but you add B prime and A prime. It has, the bracket is given as before by the same relations, ABC, ACA, BCB, but you also consider the following relations. A prime B is A prime B prime is C, A B prime is B, etc. All these are 0. So this is the brute force extension of a non-restricted Lie algebra to a restricted Lie algebra. And this has a 2 operation, meaning this is restricted, and is given by this rule. So here you are adding, so there is, in S, you do not have a restricted a 2 operation, so you add the 2 operation of A and the 2 operation of B. Okay, we had to learn this. And the restricted enveloping algebra U of M is isomorphic to K ABC over I, where I is generated by relations which I wrote in the next line. That is AB plus BA is equal to C, AC plus CA equal to A, BC plus B equal to B, and these are the powers of A, B, and this is the power of C. So this is similar to the restricted enveloping algebra of SL2, but in characteristic 2. In other words, this isomorphism, which I am mentioning here, says that the restricted enveloping algebra of M is the extension of S, is the universal enveloping algebra of S by these 3 relations. Okay? Now, some facts. First, the algebra D of H is generated by 6 elements X, Y, G corresponding to H, Y, V, gamma corresponding to H dual, and the defining relations can be explicitly stated. Second fact, there is a normal local commutative Hopf subalgebra T of D of H, such that D of H fits into an abelian extension as before. So as before, we have a local normal subalgebra T, we have the Drinfeld double, and the quotient is U of M, the algebra which I described in the previous slide. And again, T is normal and local, and therefore the category of representation, the set of irreps of D of H is in bijective correspondence with the set of irreps of U of M. And I am afraid I went too fast or prepared it too little, I don't know. So this is the end of the talk. I just want to show you the references in case you are interested in this. Thank you very much.
Any question?
So first, so you have these 2 rows, at least the bottom 2 rows in your diagrams. You said you have this triangular algebras. This was triangular triangular Hopf. So I wonder if these arrows to the
Yeah, they preserve the triangular decompositions.
They do.
Yes.
Okay, so then related question. You have quantum deformations of the U side of the enveloping algebras of SL2 and the restricted ones. Is there a quantum deformation of the Jordan plane that would fit into that diagram?
So first, the Jordan plane itself is a quantum deformation of a different kind. And the second, once this is said, the answer is I don't know, but probably not, because the Jordan block is rigid in the sense you cannot deform the Jordan block because of the classification of Nichols algebras. But this is an imprecise answer.
So more question? Slava?
In that correspondence between the reps, do you have explicit way to construct given representation?
Yes, what we do in all cases, the algebra in the middle has a triangular decomposition, and therefore you can construct the Verma modules, which are not the same as the Verma modules for the quotient, because they are bigger, of course, but you have the same recipe. You construct the Verma modules, you divide by some maximal submodule, and you get some highest weight irreducible modules, and these turn out to be those coming from the bijective correspondence I mentioned before.
Characteristic zero cases completely different.
Characteristic 0 is different. By miracle, we have the same bijective correspondence. So this is a phenomenon that appeared in this examination of these examples appeared several times, which is one has a big algebra and has a quotient algebra, and usually you will not expect that the irreps of the quotients are in bijective correspondence with the irreps of the big algebra. This goes against intuition, and in fact it happened several times. And I don't know what is the reason behind, so I don't know what is the big theorem saying that this should happen. I just observed this.
Correspondence will be in finite dimension.
Yes. Yes, because we need this lemma on the family saying that the nilpotent, the elements of the family F act locally nilpotent. It means that act nilpotently on finite dimensional representations. So this does not extend to infinite dimensional case.
Last question. Is there a higher dimensional version of multi-plane double Jordan plane?
This is a very interesting question, and in the moment I don't know. In principle, the classification we made says that if you have a block with finite GK dimension, the block should be either the Jordan plane or the super Jordan plane. Therefore, so I was expecting to have more I was expecting SL3, but I could not find SL3 yet. So if it exists in some way that I cannot see now. But there is no direct generalization of the Jordan plane. Of course, you may say, why you are asking finite Gelfand-Kilo of dimension? Take the 3 block and see what happens. Maybe, I didn't do that.
Any more questions? So, is it difficult to describe projective cover of irreducible representation in this case?
In principle, I think not, because they should come from the Verma module construction.
Okay.
Because the Verma module is, you are inducing from...
So should be like Verma module, right?
should be like Verma modules, yes, I think so. So, well, depending on where you are working. If you work in the restricted, there are several settings: the restricted Jordan, restricted super Jordan, and super Jordan. In the restricted cases, they are finite dimensional, and in the non-restricted, the projective will be infinite dimensional. Yes, like for Lie algebras.
More questions? If there are no, we should thank the speaker again.
Thank you.
And now it's coffee break, and we should